One of the universe's greatest unsolved mysteries is being investigated here in Karlsruhe. An extraordinary large-scale physics experiment is currently taking shape on the premises of the KIT, the Karlsruhe Institute of Technology. Around 150 contributors from 6 countries have gathered for this sensational project that could revolutionize the world of physics. KATRIN, the Karlsruhe Tritium Neutrino experiment, will attempt to weigh the lightest particle in the universe, the neutrino. Even though neutrinos are the most common particle in the universe, all previous attempts to determine the mass of a neutrino have failed. The experiments were not sensitive enough. KATRIN, the latest and most elaborate experiment in this series, is expected to produce the breakthrough. Scientists and engineers from the USA, Russia, the Czech Republic, Germany, Spain and France are combining their efforts to achieve this ambitious goal together. KATRIN's goal is to improve on the previous experiment's precision by a factor of 100. This means that we're reaching a multitude of engineering limits in a large variety of ways. One such engineering limit is, for instance, achieving an ultra-high vacuum better than 10 to the minus 11 millibar in a giant spectrometer tank of 1,200 cubic meters. Additionally, we're facing a large variety of engineering challenges with the source and the transport of electrons over 70 meters. If you want to improve on the sensitivity of past experiments by a factor of 100, you really end up breaking new engineering ground, among other things in the fields of ultra-high vacuum technology, tritium technology, and voltage stabilization, where we need to stabilize a voltage to about 1 part in 1 million. There are many different challenges. KATRIN will be more sensitive and more precise than any of its predecessors, whose experiences are part of the planning surrounding KATRIN. The new experiment will stand several stories tall and will be over 70 meters long. It is a highly complex installation, every part of which pushes the limits of what is possible. Yet KATRIN will be nothing other than a scale, albeit the world's most sensitive scale. And this is how KATRIN works. In this experiment, scientists observe a radioactive process with unprecedented precision. The neutrinos to be weighed are released in what is called beta decay. Neutrinos themselves are not directly tangible. They elude direct observation and effortlessly penetrate any matter. But there is a way to reach conclusions about the mass of neutrinos indirectly, from the energy of the decay products. Why is such a massive effort underway? Why is the neutrino so important to these scientists? The neutrino is a true phantom particle. Even though it is the most common elementary particle in the universe and accounts for a significant portion of the mass of the visible universe, it stubbornly resists direct observation. As early as 1930, Nobel Prize laureate Wolfgang Pauli postulated the existence of the neutrino, a minuscule particle without any electric charge that would go on to cause trouble for physicists over the years. In postulating the neutrino, Pauli did something outrageous, for he knew that its existence would be incredibly difficult to prove. Neutrinos cannot be slowed by the Earth, by the Sun, not even by entire galaxies. In this respect, he was aware that it would probably take a very long time for this particle to be proven to exist. And then it took more than a quarter of a century until experiments could be run on these neutrinos. Many physicists were certain that it would never be possible to detect neutrinos. It was not until 1956 that an American team proved that neutrinos are created during the fission of uranium nuclei. Today, we know that neutrinos are ubiquitous in the universe. Each cubic centimeter still contains 336 neutrinos from the Big Bang, and neutrinos are created in many astrophysical processes, in stars, in collapsing black holes. And we can use neutrinos as probes to look into areas we would not have access to otherwise. The nearest large source of neutrinos is the Sun. 60 billion solar neutrinos penetrate each square centimeter of our bodies every second without consequences, because there's virtually no interaction with matter. Physicists know from the neutrino oscillation observed in solar neutrinos that neutrinos are not massless, but must have an extremely low rest mass. And this mass must have played a critical role when the structures of the universe formed in its early days. To this day, neutrinos herald monumental cosmic events. In 1987, astronomers discovered a giant supernova in a neighboring galaxy of the Milky Way. A few hours before the light of the explosion reached Earth, multiple neutrino observatories independently detected a massive neutrino emission. But even 70 years after Wolfgang Pauli's neutrino postulation, nobody knew how much a neutrino weighs.
One of the surprising issues is, why are neutrinos so light? They're basically 250,000 times lighter, at least, than electrons. So, you know, the electron, up until we knew neutrinos had mass, was the lightest particle we knew about. And the fact that neutrinos are 250,000 times lighter is something we really don't understand why. So that's something that once we have determined what that mass is, that's going to maybe help us solve the riddle of what is the origin of mass and why the particles have masses that they do.
Previous attempts to determine a neutrino's mass failed due to the insufficient sensitivity of the measuring equipment. The Karlsruhe experiment will now be more sensitive by a factor of 100. Accordingly, the component's dimensions are much bigger as well. The giant spectrometer tank was a special challenge for the planning team. The tank was manufactured by a physical systems engineering specialist in Deggendorf, Bavaria. They used special, particularly low radiation steel in its construction. The precision required for assembling its component parts could only be guaranteed on the manufacturer's own premises. Assembling the parts in Karlsruhe would have delayed the project by 2 years and would have required the construction of its own assembly hall. And so, the spectrometer tank was built 400 kilometers away from Karlsruhe in Deggendorf. With insurmountable obstacles in the way, transporting it by land was out of the question. The tank was too big and too heavy to transport it through Germany's streets. The only other option was transportation by water. On September 28, 2006, the tank embarked on its journey on an inland vessel. The journey takes it down the Danube to the Black Sea. It continues by cargo ship, first to the Mediterranean Sea, through the Straits of Gibraltar, into the Atlantic Ocean, all the way to Antwerp, an 8,400-kilometer detour. In Antwerp, the tank is reloaded from the cargo ship onto a pushed train. It travels upstream on the Rhine to the Eggestein-Leopoldshafen inland port near Karlsruhe, where Europe's largest mobile heavy-duty crane awaits the transport and transfers the spectrometer tank to a special-purpose vehicle. It travels only the last 7 kilometers to the site of the former Karlsruhe Research Center, today's KIT, by land. A spectacular transport, and meticulously planned down to the last centimeter. After a journey of more than 8 weeks, the transport finally arrives at the research center. There, the specially built experiment hall has already been unroofed so that the tank can be installed safely. The hall's concrete is particularly low in radiation, because even the comparatively low natural radiation of building materials would compromise the spectrometer's measuring precision to an inadmissible degree. The KATRIN experiment's purpose is to study the radioactive decay of gaseous tritium, a heavy isotope of hydrogen, more closely than ever. During what is called beta decay, a neutron splits into a proton, an electron, and a neutrino. But there is no way to measure a neutrino's mass directly. Instead, the scientists measure the energy distribution of the electrons and make an indirect conclusion regarding the neutrino's mass. Superconducting magnets direct the electrons released during beta decay into the energy analyzer. Low-energy electrons are filtered out. Only high-energy electrons are of interest to the scientists. Only 1 in about 100 billion electrons reaches the detector and is registered there. A particularly strong tritium source is needed to ensure that enough electrons reach the detector and that the experiment can be completed in a reasonable time frame. This is also the reason why the experiment is set up in Karlsruhe. Only KIT has the necessary tritium technology and a sufficiently powerful tritium source. The Karlsruhe Tritium Laboratory has already developed the fuel cycle for the ITER fusion reactor. The isotope laboratory's infrastructure and its expertise for handling larger amounts of tritium gas are now being used for the KATRIN experiment. The laboratory also developed the pump system for the closed tritium loop of the windowless tritium source. This pump system prevents radioactive tritium gas from escaping the source. While the electrons are extracted from the tritium source using a strong magnetic field, no radioactive tritium may enter the spectrometer tank under any circumstances. Otherwise, the radiation would disrupt the measurement. Tritium gas is injected into the tritium source, where a complex cooling system cools it down to exactly -243 degrees Celsius. It maintains the temperature to within a few thousandths of a degree during the entire measurement period using a liquid neon coolant. Superconducting magnets produce a strong magnetic field, keeping the electrons on course on their way through the source. Well, here we're going to insert a very stable tritium gas flow into the center of the beamline. There, the gas will spread evenly, drain through these big pump ports. During its time in the beamline, all the natural beta decays will occur automatically. And these 7 big magnet modules grouped here will then guide the signal electrons in this direction towards the spectrometer. So if this doesn't run properly, the experiment won't work. While the tritium source is still undergoing intense work in Bergisch Gladbach, the cryogenic pumping section arrives at the KIT. Along with the differential pumping section, this will connect the tritium source to the pre-spectrometer. It is moved into its final position, floating on air cushions. A little later, the 16-meter-long tritium source, weighing over 20 tons, has also arrived in Karlsruhe and is lifted into its place with utmost precision. The tension is visible on everyone's faces. If everything works as calculated, this radioactive source will be the experiment's cold heart from now on.
Well,
today we've reached a very big milestone with the delivery of the source, which we've just installed here. We've been working towards this day for over 12 years. This is the final large component we need to set up this great experiment. This whole thing has taken so long because we were breaking new ground in the areas of cryotechnology, vacuum technology, and superconducting magnet technology. What we put together here has never been done before anywhere else, and now we're very proud to have made it this far, with all of our partners, with all those scientists around the world, with all of the collaboration. The magnets of the differential and cryogenic pumping sections guide the electrons from the tritium source to the spectrometer. Turbomolecular pumps and cold surfaces near absolute zero remove the last traces of tritium gas, which is returned to the closed loop. A few years earlier, in the spectrometer hall, 3 specially developed pump systems are installed in the lowest level of the large experiment hall. At a pumping speed of up to 1 million litres per second, they are to create an extreme vacuum within the spectrometer tank, the likes of which can only be found in space. The vacuum tests take months to complete. Then it is clear the tank meets all expectations. But the tank is only the vessel in which a highly complex interior has been installed. In the cleanroom of the University of Münster, a highly precise wire electrode system for the main spectrometer tank is being developed. A total of 42 kilometers of stainless steel wire will generate a stable and accurately defined high-voltage field inside the tank. For this purpose, the wires are mounted on specially designed brackets. A laser is used to confirm whether the strict precision requirements have been met. The wires may not sag more than 1/5 of a millimeter. Another development by the Münster researchers, the high-voltage divider. It measures the high voltage for the electrode system in the spectrometer tank. The voltage stability requirements are immensely strict. The tolerance 1 in a million. In the United States, at the University of Washington in Seattle, scientists have developed a detector system to be installed at the main spectrometer's output. A magnet system consisting of 2 superconducting magnets ensures that the electrons carrying information about the mass of a neutrino are focused and make it to the actual detector.
I have a long personal involvement with the neutrino. I worked at Los Alamos myself for some 13 years, and we did an experiment there to try to measure the mass of the neutrino. We did not find a mass for it, but we were able to show that the neutrino is a relative lightweight in the universe, and we would like to know just how light it is. We know that it's not completely massless.
Only the experiment itself will show whether KATRIN's sensitivity is high enough to measure the mass of a neutrino. Designing every component of the experiment to be as precise and accurate as possible is a major challenge for engineers and scientists.
What makes it such a wonderful experiment, in my mind, is the simplicity of the idea of what we're doing. We're going after a very specific goal that's understandable, and the way in which we're going after it is understandable. But it's at the same time requires amazing technical challenges, and you get to see people on the ground constantly designing new things and understanding how you can make the best measurement you can possibly make. And it's exciting to be a part of that, to be able to contribute to that.
The actual eye of the experiment, the detector. A silicon disc with a diameter of 10 centimeters and a thickness of only 1/4 of a millimeter. A highly sensitive semiconducting detector developed specifically for KATRIN. Its surface contains 148 detector cells registering the electron flow over the course of several years. Even if the neutrino turns out to be too light, KATRIN will be a success.
This experiment is so technically demanding. We have really invented a lot of new technologies to do this. And as you invent the technologies, our goal is really just to do this experiment, but it turns out that a lot of these technologies might actually be useful to people.
MIT in Boston. In February 2010, members of various teams meet for a workshop. Monte Carlo simulations are to be run to anticipate the experiment. Not its results, those can only be gained from the experiment itself, but the way there. What will the detector measure? What will the data reveal? How should the test results be interpreted? Experimental physics meets theoretical physics. Scientists converse with programmers and engineers. Different disciplines work together to achieve a common goal.
The idea behind forming the collaboration was to really take that international expertise that had been developed, and instead of trying to compete against one another and not do as good a job, was to take that expertise and combine it into essentially a single international experiment.
The point is that complex experiments like the KATRIN neutrino mass experiment have to be simulated very accurately on computers in order for its very complex data to be understood properly. Experts, young and old, from all around the world meet here to discuss this massive Monte Carlo project and to distribute and carry out the individual work packages.
You can already see, the level of engagement and ideas that people going back and forth, and this is exactly what I was hoping for this workshop, and I'm very pleased to see that that's exactly what's happening.
In Karlsruhe, work proceeds. The main spectrometer's tank is surrounded by a system of magnetic coils by now. They compensate for the terrestrial magnetic field, so that an accurately defined electromagnetic field can be generated inside the tank. Autonomous magnetic field sensors periodically travel along the magnetic coils, measuring even the smallest deviations in the magnetic field to be taken into account in the analysis later. Meanwhile, the electrodes from Münster are being installed inside the spectrometer. We have to fit 690 square meters of inner surface of the KATRIN spectrometer with ultra-precise, vacuum-friendly electrodes suited for ultra-high vacuum. That's 2 wire layers aligned to a precise 200 micrometers relative to each other. And we have to maintain this alignment even after heating it to 350 degrees Celsius. No impurities may enter the tank during the fitting of its interior. Any dust, any impurity would later impair the extreme vacuum conditions and contaminate the tank with natural radiation. This would compromise the measurement's accuracy, which is why the technicians are doing their work wearing cleanroom suits. The electrodes are mounted on specially developed frame brackets and are now fitted to the tank's interior. After years of very focused high-precision work, the electrode system is finally installed, along with the large vacuum pumps, called getter pumps, which are responsible for creating and sustaining an extreme vacuum comparable to that of outer space. Now the lids are closed and the pumps can commence their work. Additionally, the tank is heated to temperatures of around 300 degrees Celsius in order to catalytically clean its interior. Without this process, it would be impossible to generate such an extreme vacuum. After the first spectrometer tests, the final components are adjusted and moved into position. A series of test measurements serves to determine how well the individual components work together and whether the, as yet only theoretically functioning experimental setup can actually produce usable results. Only when everything works exactly as intended can the tritium gas be fed in. A process that cannot be reverted should an error have snuck in. The big moment has arrived. First light. And KATRIN is active. Our goal for first light was to transport the first electrons through KATRIN over a distance of 70 meters. And for that, many components we received only last year had to be connected after long years of setup. They had to be cooled to very, very low temperatures. Electricity had to be applied to the magnets. There were many tasks we performed in parallel. We had to implement the control systems. We had to make sure that all of these components had been combined into a sensible setup as a whole. And in that respect, we never felt that the days and nights were long enough for us to actually achieve this great goal, first light, which we've achieved today. This was an outstanding performance by the team, and I think we really owe to the team the fact that we actually still made it.
Today, it all came together and electrons were sent through from one end to the other, and now we are ready to start commissioning the whole experiment as a single unit to try to measure the mass of the neutrino.
After a projected 5 to 6 years of measurements, during which measurement data will be collected continuously, the researchers could have an answer to the question, how much does a neutrino weigh? But KATRIN will have an effect beyond that. We noticed that all of this is much more complex, much more challenging. You need much more stamina. You basically need much more expertise. And we did assemble this expertise by searching around the world and looking to see who has this expertise. In that regard, we discovered many new things. We basically got to know completely new processes. And even if KATRIN is basically just a somewhat bigger experiment than the existing ones, our great sensitivity has made us aware of processes and phenomena no human has ever seen, and which were not even on our radar 15 years ago when we first planned this experiment. In that regard, it always stays exciting, and I think it will stay especially exciting in the next few weeks, days and months until we've measured the neutrino's mass. A measurement like KATRIN, which is so precise that this narrowing down of the neutrino's mass is cosmologically relevant to considerations in particle physics, this will go down in the textbooks, and it'll become part of future lectures.